Hey guys, in this video we're going to talk about Chapter 16, Section 4, Double Integrals in Polar Coordinates. Okay, so the reason that we are changing into a different coordinate system is because we're going to come across integrals that look something like this, that are way too hard to integrate with respect to x and y. So the idea here is to change a super complicated integral into something that's not so complicated by changing the coordinate system. And to do that, we're going to go from what's known as Cartesian or rectangular coordinates, which are x's and y's. So rectangular / Cartesian. This is going to be x's and y's. And the idea is that we're going to change this to make our integrals look a little bit simpler into r's and thetas, where r is representative of radius, the word radius, and theta is an angle. Okay, so we're going to go from rectangular to polar. We call r's and thetas polar. So... and you may not have seen this for a while. You definitely saw it in trig. If you took, obviously all of you guys have taken trig. But I'm going to give you guys just a little review on how we deal with polar coordinates. So again, what we're trying to do is we're trying to change everything from x's and y's into r's and thetas. And these are the identities that we can use to do that. And where did these identities come from? Well, they just come from right triangle trigonometry. So remember that, if we draw a little right triangle on the plane like this, so we have so this is like our positive x-axis right here, and we have this angle theta that is made with the positive x-axis and the hypotenuse of this triangle. We have our x component, so how much we're going horizontally right here. We have our y component, which is our vertical component of the triangle right here. And we know that the cosine of an angle is the adjacent over the hypotenuse. Now, what's the hypotenuse going to be? Well, assuming that we're drawing this triangle on a circle like we did in trig, the hypotenuse is going to be our radius. Now in trig we looked at the radius being 1 all the time. We looked at points on the unit circle because that made our calculations a lot easier. But here the radius can be whatever it wants. So we can think of this as like the center of our circle, and r is the radius of our circle. Okay, so yeah, and of course that's a terrible circle, but you guys get the idea. That is the radius of our circle. So just using basic Pythagorean identities and right triangle trigonometry, we can derive these identities up here. We can say, okay, well, I know that cosine of theta is adjacent over hypotenuse. So adjacent of theta is x and our hypotenuse is r. And so we have cosine of theta is equal to x over r. And if I isolate x by multiplying both sides by r, I get x equals r cosine theta. And we can do the same kind of thing with y to get that y is equal to r sine theta. And then to get this identity down here, x squared plus y squared equals r squared, well, you would just use Pythagorean theorem here. Okay, so that is how we get these identities right here. So the idea is wherever we see an x, we're going to sub it in with r cosine theta. Wherever we see a y, we're going to sub in with r sine theta. And then x squared plus y squared is equal to r squared. So the idea is that, when you're in the xy coordinate system, So when you're in the XY coordinate system, and I just give you a random point right here, P, I can describe that by saying how much I go to the right and how much I go up. Okay, so I can describe that with XY values. But so I can also describe that in the sense of I can say, okay, well, that point is going to be a certain radius away from the origin, right? So it's going to be some radius away from the origin, and it's also going to make some angle, right? It's going to be at some angle with the x-axis. So that's the idea. So instead of saying, okay, go right, so many units, go up so many units, this time we're saying go out from the origin, r units, right? And then go an angle of theta away from the x-axis. We can describe a point in that same kind of way. Okay, so let's practice describing regions in polar coordinates. So region is just a set, right? And so we want to be able to describe any kind of point that is lying in the set. We want to be able to describe that point. We want to be able to describe that point, that point, that point, that point. All of these points with polar coordinates. We want to be able to describe it with an r and a theta. So where can r range in the set? Well, I could be on the boundary of the set. I could be way out here. I could have a point there. That would be included, right? Or I could have something right here, maybe a little bit closer to the origin or something like that. So we want to describe a lower and an upper bound for the radius of where these points will be on. Because this point right here is going to have a small radius versus this one right here is going to have a bigger radius. So where could that radius vary? Well, we could have a guy right here smack dab in the origin, so that would mean that r would be greater than or equal to 0. Or we could have some guy right here, or we could have some guy way out here to the boundary. Well, what is this radius right here? What is the maximum radius that we can have? Well, since the radius is the distance from the center to the edge, we can just count up from the center up this way if we want to. 1, 2, 3, 4. So this is a radius of 4. Okay, so we're going from 0 to 4. That includes, not r, 4. That includes all possible radius of these radii of these points in the set. And now we want to describe theta. So what could theta be? Well, if we're right here and we haven't moved, or maybe if we're right here and we haven't moved, or right here, if our point is right here, theta is going to be 0, right? But as we move along the circle, theta can change, right? So here is theta is pi over 2, here theta is pi, 3 pi over 2, and 2 pi. So theta can be anything between 0 and 2 pi. That could be our angle from the x-axis. Anything between 0 and 2 pi. And that's how we describe this region in polar coordinates. So it's just a circle of radius 4 centered at the origin, and this would be how we could describe any point in that set using polar coordinates. Okay, so let's try this one. So now it looks like we have a quarter circle. So anything in this region could be a point in our set. And we can see that they tell us what the radius is. The radius is square root of 3. So from the center to the edge is r equals square root of 3. So that's going to tell me that my radius is varying between 0 and square root of 3. Now, where is theta varying? Well, theta can be 0, certainly, because all of these points are included in our set. And as we move along, so as we change theta, we're going to end up getting a maximum value of theta, which right here is pi over 2. So that's going to be, this is our maximum value of theta. And so theta is going to range between 0 and pi over 2. And this is how we could describe this region in polar coordinates. All right, what about this guy? So I encourage you to pause the video at this point, see if you can do this one. We need r and theta to describe this region. So this is a half circle, and you know, any point in this set will do. So how can we describe any point in this set with just a radius and a theta? Well, this point is in the set, right? And that guy has a radius of 0. So we're going from 0 to, what's the maximum radius I can get? Well, I can just figure out what this point right here is. Or if you look at it on the x-axis, it'll just tell us that our radius is 8. Right, so that's the distance from the center to the edge of the circle. So our maximum radius that we can have is 8. And theta is going to vary between 0, because this is where the minimum angle can be. And then as we move along the circle, our angle is going to get, it's going to increase all the way until pi. This is our maximum angle that we can have. So theta is varying between 0 and pi. Okay, so that's how we can describe this region in polar coordinates. Now, what about something like this? Well, here, notice that this part is not included in our region. It's not shaded. So we don't want to start at a radius of 0, because this guy would have a radius of 0, and that's not included in our set here. So we want to start where the minimum radius is, which would be something right here. Right? So this is our minimum radius. Okay, so that is going to start at a radius of 4. So we're starting right off the bat with a radius of 4. So something that has a radius of 2 would not be in this region, and that would be something in this area, right? So this would have a radius of 2. But we're not including that. So we're starting at a radius of 4, and the maximum radius that we can have is right here at a radius of 8. So this is our circle. This is an arc of a circle with radius 8. So this is our max radius. So we're going from r equals 4 to r equals 8. We cannot describe, we can describe a point in this pink region with radius between 4 and 8. Okay. That's our upper bound there. So what would our theta be? So where would our angle range from? Well, again, you know, you measure theta from the origin. You kind of throw a ray out there and then see which angle it sweeps out. So, you know, this guy would correspond to theta equals 0. And then it's going to sweep out this pink shape. And it's going to sweep it all the way up here until theta is equal to pi over 2. So those are my bounds for theta. So this is how we can describe this region just using a radius and an angle theta. All right, let's go in the opposite direction and sketch the region. So we have our region is r theta. R varies between 0 and 2, and theta varies between 0 and 2 pi. So we can go the opposite way this time. So since my radius goes from 0 to 2, I'm going to just mark 2 right here, and a little point right there, and then here at 0, we have, at y equals 0, we have 2 there, and we have -2, negative 2. Remember, our radius, when we talk about a radius, we don't think about it as being negative. We can say that our point is at a negative position, but we don't really talk about a radius being negative. Because radius is, we talk about distances with a radius. So my radius is 2, and my theta, my angle that it's going to sweep out, is 2 pi, right? So what that means is that this whole, it's a terrible circle. But anyway, this is our circle right here, and our region is going to be everything shaded in the circle. So everything varying from 0 to 2 pi for my radius, and theta is going from 0 to, sorry, my radius is going from 0 to 2, theta is going from 0 to 2 pi. Okay, so what about this region? So now we have our radius is varying from 1 to 3, and our theta is going from 0 to pi. So here's 0, here's pi. My radius doesn't start until 1. So here's 1. And it's going to end at 3. So maybe I'll extend this a little bit to 3. And here's negative 1, negative 3. All right, so we're starting at 1, and we're going to 3 with our radius. And so what this is going to look like, it's going to just sort of look like a band. So our radius is 1. We're going from 1 to 3. And we're sweeping this out through an angle of pi. So we're starting at theta equals 0, and we're sweeping it out until theta equals pi. So our region is going to be this guy shaded in red. So let's do some practice converting rectangular coordinates to polar coordinates, because we're going to be dealing with some ugly integrals, and we want to make these integrals as simple as possible. So remember our identities. We have x equals r cosine theta. We have y equals r sine theta. And we have x squared plus y squared equals r squared. So all of these can be used to convert back and forth between rectangular and polar. Now I see x's and y's. So let's go ahead and sub in x is r cosine theta and y is r sine theta in for x and y. So x, we have r cosine theta squared plus y is r sine theta squared equals 9. And then if I square both of these things in parentheses, I get r squared cosine squared theta plus r squared sine squared theta equals 9. And if I factor out an r squared, I'm left with r squared times cosine squared theta plus sine squared theta is equal to 9. Now, from trig or calc 1, or whenever the last time you saw this, calc 2 if you took me, cosine squared plus sine squared, this is a special identity. It's a Pythagorean identity, and this equals 1. So this is important. You'll probably use this in your homework at some point. But we're going to go ahead and make that substitution here to clean it up even more. So we get r squared times 1 is equal to 9, therefore r squared equals 9, and therefore r equals 3. We're not going to take negative 3 because, as I said, the radius is not really like a negative kind of concept, it's distance, so we're just going to leave it as r equals 3. So these two things describe the same thing, the same exact thing. It's just the circle that has a radius of 3. So, and it's centered at the origin. So anything, and it doesn't include the inside of the circle, by the way. It just says x squared plus y squared equals 9. This is a circle with radius 3. centered at the origin. And so the only points in our set is going to be all of these points on the boundary of the circle. Okay, nothing inside is included here. R equals 3 is the circle centered at the origin with a radius of 3. Okay, let's try the next one. So we have y equals 3x plus 2. Now, we all know, hopefully, if you're watching this, but if you don't, it's okay too, I guess. We all know that this is a line with slope 3 that goes through a y-intercept of 2. Okay? That was from algebra. Now, what is this in polar coordinates? How do I describe this line in terms of r and theta? How do I describe it? Well, again, we're just going to use these identities to sub in something for x and something for y. So y is equal to r sine theta, so we get r sine theta is equal to 3r cosine theta plus 2. So I can, kind of manipulate this if I want to. And, I could leave it like that. That would be fine. But if I group the r terms together, what I can do is I can subtract 3r cosine from both sides to give me r sine theta minus 3r cosine. And on the right side I get 2. If I factor out an r, I get sine theta minus 3 cosine theta equals 2. And then I can solve for r. So I can get my r is in terms of theta. It's a function of theta. And it's going to be 2 divided by sine theta minus 3 cosine theta. And that's my answer in polar coordinates. I only have r's and thetas. So, that's it. Okay, let's do another one. So we have x squared plus y squared equals 6y. Anytime you see an x squared plus y squared grouped together like that, you should think, okay, I'm going to use this identity right here, this r squared. And actually, I probably should have done that to begin with. I made a mistake in doing more work than I had to, but maybe this was good to show you because you might have done the same thing on your homework. You can use these and you're going to get the same answer using the Pythagorean identity, but why not just skip a step and say, well, x squared plus y squared equals r squared. Let's go ahead and plug that in from the jump. I should have done that for number 1, but, maybe this was useful to see it like this. I don't know. Anyway, x squared plus y squared is r squared. Let's go ahead and sub that in. And y, the only thing we can sub in for y is r sine theta. So this is going to be 6 times r sine theta. And what I can do is I can, if I want to just get things, if I want to isolate r, basically, what I can do is I can subtract that 6r sine theta from both sides. And I get this guy. And now what I can do is I can factor out an r. So you kind of have two choices here. You can say, okay, well, r equals 0, or if I set this piece equal to 0, I get r equals 6 sine theta. All right, so that's how I can represent this region right here in polar coordinates. Let's go ahead and do this one down here, x equals 4. Now we all know what this is, I hope. This is a vertical line that goes through x equals 4, just like that. How can we say what this is in polar coordinates? How can we describe this? Well, x is equal to r cosine theta, so we have r cosine theta is equal to 4, so r is equal to 4 over cosine theta, and that's how we can describe that region just using polar coordinates. Now notice theta is free to vary, right? And r is going to depend on theta, and also r can't be negative, so that's something if you want to explore this a little bit more. You can, play around with the values of theta and see what you get for r, and, just compare it to the picture that x equals 4, right? Compare it to this picture. But we're not going to do that now just because we don't have time for that. What about something like this? Well, I see an x squared and a y squared, so I'm not going to make the amateur mistake that I made in number 1 and start subbing in r sines, r cosines. I know better than that. I can go ahead and add that y squared to both sides, and I get this. And now I see, oh, well, this is r squared, so I can make that substitution to get r squared minus 8 equals 0. So if I add 8 to both sides, I get r squared equals 8. Take the square root, and I get r is equal to square root of 8, which you can simplify if you want. It's not really necessary. But if you do, this is going to be, let's see, it's going to be 2 square root of 2. Right, because 8 is 4 times 2, 4 is 2 times 2 times 2, take out a 2, yeah. Alright, so r is equal to root 8. So this is just a circle centered at the origin with radius root 8. Yeah, that's pretty much it. So the region just looks like this. And remember, this is when we have r by itself, we're just talking about this boundary. We're not talking about the inside stuff. So this is a circle with r equals radical 8. So let's say that we're trying to integrate a function with 2 independent variables, x and y, over some region r. Well, keep in mind how we did that before when we just had x and y in as our variables. What we did is we looked at the region on the xy plane and we divided it up into very small rectangles. Okay, we took the area of those rectangles. So the rectangles had dy dx as the dimensions, dy dx. And we took the area of the rectangle and we multiplied it by the height. And the height corresponded to the function being evaluated at x and y. And then what we got when we did that was a volume. And what we did is we added up all of those rectangles on that region, added up all of those volumes to get the volume of the figure, whatever we were trying to take the volume of. Now, what I want to do here is I want to convert everything that I know about Cartesian integrals like this and change them into polar. So I want to eliminate x and y, and I also, x and y basically. So let's say that I have this function that I'm trying to take the double integral of, and I'm integrating over some region on the xy plane. And suppose our region looks like this little pink circular arc thing. Well, what we did before, as I just mentioned, is we took that region and we divvied it up into these, infinitely small rectangles, right? You want to pretty much imagine that these rectangles are so small that you can't see the length or the width of them. But because of that, because of, the fact that they're so small, we said that the length was dx and the width was dy, so the change in y and the change in x, just a little bit. And to find the area of such a rectangle, well, you just multiply dx by dy, because the area of a rectangle is length times width. So that's how we got dA. That was our area there. And the volume of a figure is just the area of the base times the height. And so again, what we did is we took the area of these really small rectangles, multiplied by the height, which corresponded to that function being evaluated at a particular x and y. So that's how we found the volume. Now, let's go ahead and look at this little rectangle right here zoomed in polar coordinates. So this rectangle, this DA, is actually the same one I have in light blue off to the side. Okay, so in polar coordinates, we can describe this rectangle just as well with r's and thetas. So our rectangle is going to be in quadrant 1. We can see that here with our region. And it's going to, it's going to be theta away from the x-axis. And we have this small change in theta right here, this d theta. We also have a radius going out from the center. So from the origin to the edge right here. And then this guy, this remaining piece, is going to be the radius plus a little bit more, right? So this little green piece is going to be dr. And this guy is going to be r d theta. And why is that? Well, if you remember from trigonometry, we had this formula. We had an arc length formula. And it told us that the arc length was equal to the radius times theta. So the angle that intercepts it. The angle that intercepts this guy right here is d theta. That's the angle there. And of course, our r is just going to be r, right? Because that's the radius that intercepts this arc. And so that guy is just going to be r times d theta. That's why this little guy is r times d theta. Okay, so now, we've turned this rectangle into polar coordinates. We have polar coordinates now. So we have that the area of that rectangle, well, instead of dx dy, now what do we have for our dimensions of the rectangle? We have r d theta is the length, and dr is the width. So the area becomes r dr d theta, or you can write r d theta dr and just move the r to the front. But this is the idea. This is how we're going to change our dx dy into r dr d theta. So dA, before we knew it was dx dy, and now in polar coordinates it's r dr d theta. Okay? So instead of writing this is in Cartesian or rectangular. Instead of writing that, we can write the same thing by saying, okay, instead of x and y, in here I'm going to write f of r cosine theta, r sine theta, and instead of writing dy dx, well, I'm going to write what I just derived. I'm going to write, instead of dy dx, I'm going to write r dr d theta. So this is polar. Oh, I already wrote it up here. Whoops. But that's the idea. So let's do this in practice. So we want to evaluate the integral over a region, and our function is 1 minus x squared minus y squared dA. Okay, so in rectangular, remember dA, the change in area, is the change in x times a change in y, but we're about to change to polar. It says that R is the unit circle on the xy plane. So that's going to tell us where our bounds for R need to be and where our bounds for theta need to be. Okay, so the first thing I'm going to do is I'm going to change my x squareds and y squareds in terms of r's and thetas. So now I can factor out a negative so that I have 1 minus x squared plus y squared. And instead of dA, remember what I'm going to write as my new polar components. dA is going to be r dr d theta. So that's what I'm going to write here. I'm going to say this is r dr d theta. And now I'm going to use the fact that x squared plus y squared is equal to r squared. So So I get 1 minus r squared, and this is all being multiplied by r dr d theta. Okay, so that's set up. Now I want to go ahead and set up my bounds based on my region. So it says R is a unit circle on the xy plane. That's the region of integration. So since I'm integrating with respect to R first, my radius, so this is my region, and we're going to assume that integrating all of this. So this is my unit circle. This is my region. And it has a radius of 1 because it's a unit circle. So my radius is equal to 1. So how do I say that in terms of where the radius varies? Well, anything on this in this set can go from r equals 0 to r equals 1. So I'm doing the radius first because dr comes first. And then theta, well, this sweeps out the entire circle, so we're going to go from 0 to 2 pi. All right, so this is the setup, and the setup is always the hardest part. Like, I think so anyway. The bounds, getting the bounds right is always the hardest part. So, you can always draw a picture or look at GeoGebra to help you out, but that's what we have so far. And let's go ahead and do this. This is always the easy part, I think, just evaluating the integral. If I distribute that r in there, I get r minus r cubed. We're going to integrate with respect to r first, and then we're going to integrate with respect to theta. So let's do the partial with respect to r. When I do that, I get r squared over 2 minus r to the 4 over 4, and I'm going from 0 to 1. And the 0 is nice because it's going to cancel at that second piece of my integral. So I have 1 over 2 minus 1 over 4. So that's going to be a fourth. Oh wait, yeah, that's a fourth. 1/2 minus, yeah, okay, good. All right, so that's what I get there, and I still have to take the integral of this. Well, I have to use the outer integral. So I'm going from 0 to 2 pi of a fourth, and this is going to be with respect to theta. So with respect to theta, this just becomes a fourth theta when I integrate, and I'm going from 0 to 2 pi. So 1/4 times 2 pi. 2 pi over 4 reduces to pi over 2. And then when you plug in 0 for the other one, you just get minus 0. So this is our answer right here, okay? That's how we can use polar coordinates to figure out harder integrals like this one. All right, so we want to integrate x plus y over the region described below. Again, the region, where we're integrating, it's always the hardest part to figure this out. So what I encourage you guys to do throughout this video is pause it, try to see if you can figure out the region. That's always the hardest part. Okay, but the easy part is getting this stuff in terms of r's and thetas. So again, dA is equal to r dr d theta, which equals dy dx, or dx dy. So that's good. And then x is equal to r cosine theta, y is equal to r sine theta, and x squared plus y squared equals r squared. So this is the stuff we have to work with. So let's go ahead and change the inside first. Let's just leave the region alone for now. Okay, so instead of x, I'm going to replace x with r cosine. And instead of y, I'm going to replace y with r sine. So this becomes r cosine theta plus r sine theta. And then instead of dA, I'm going to replace that with r dr d theta. Or r dr d theta. Don't forget that other r. That's important. Okay, cool. All right, at this point, what I'm going to do is I'm going to factor an r out and just kind of clean this up a little bit. So we have region r, factor out an r. I'll move this other r to the front so it becomes r squared in the front. And then what's left is the cosine theta plus sine theta dr d theta. Okay, now let's figure out what the bounds are. Okay, let's figure out what this region is described as. So this is what it says. It says, okay, the region is the set x, y such that x squared plus y squared is greater than or equal to 1, but less than or equal to 4, and x is less than or equal to 0. So to get the geometric picture of what this looks like, I'm going to change the set itself into r's and thetas. So, so I have, well, maybe I'm just going to look at this portion right here. Okay, so this portion is going to be, well, instead of x squared plus y squared, I have r squared varies between 1 and 4. And then instead of x, I have r cosine theta is less than 0. Right? Instead of x, I have r cosine right here. And instead of y, I have r sine. So, up here, if I want to get r, if I square root everything, I get r is bigger than or equal to 1, less than or equal to 2. Okay, so that's one little nugget of information that I have there, is where my radius can vary. That's nice. And then this little piece right here, I'm trying to figure out what theta is from this piece. So to figure out what theta is from this piece, how about I divide both sides by r to give me cosine theta is less than 0. And, less than or equal to, I'm sorry. And when is this true? When is it true that cosine of theta is less than or equal to 0? In which quadrants? Well, that's going to be true in quadrants 2 and also quadrants 3. And it's also going to include this pi over 2 and this 3 pi over 2 because it can be less than or equal to 0. At this spot and this spot, its cosine is 0. It is equal to 0. So this is where my theta is going to vary. It's going to be between pi over 2 and 3 pi over 2. Okay? So now I have everything I need to know. Cool. So I have, and maybe I'll write this out right here, thus theta, well, let me do it down here. So theta is between pi over 2, including pi over 2, and 3 pi over 2. So these two things that I have boxed are the things that I need to know for my bounds. You see what I mean? Why it's the hardest part? Because it's like you look at this and you're like, I don't know what you're talking about. You kind of have to reason through it. Anyway, so since I am integrating with respect to r first, I'm going to put my r bounds on the inside. So that's going from 1 to 2. And on the outside are my theta bounds. I'm going from pi over 2 to 3 pi over 2. So let's go ahead and do the integration. So with respect to r, that means that this stuff can be treated like a constant. Okay, that's nice. So this just becomes r cubed over 3, and then this just comes along for the ride since it's constant. Okay, and we're going from 1 to 2, And again, if it helps you, you can plug in that r equals to know, oh, okay, I integrated with respect to r. I'm plugging these in for r, not theta. So, and maybe I'll just carry everything else down here. This is all d theta. Okay. All right, so let's go ahead and plug in 2 for r. So we have 2 cubed over 3 cosine plus sine minus 1 cubed over 3 cosine plus sine. Okay. So what is this? This is 8/3 minus 1/3. That's 7/3 cosine theta plus sine theta. And now we need to integrate this again with respect to theta this time, going from pi over 2 to 3 pi over 2, d theta on the outside. So if I integrate, well, first of all, I'm going to pull out the 7 over 3 because I just don't want to deal with it. So let's pull that guy out. And if I integrate cosine, what do I get? Well, I get sine. So when I integrate cosine, I get sine. When I integrate sine, I get negative cosine. And this is going from pi over 2 to 3 pi over 2. And I still have the 7 over 3 on the outside. Okay, so let's see. If I plug in 3 pi over 2, I have 7 over 3 sine 3 pi over 2 minus cosine 3 pi over 2 minus, now I plug in my lower bound, and now I'm running out of room. Oh, that's as far as I can go. I'll just write it down here. Minus sine of pi over 2 minus cosine pi over 2. Okay, so sine of 3 pi over 2 is negative 1 from the unit circle. Cosine 3 pi over 2 is 0. And then sine of pi over 2 is 1 from the unit circle. Cosine of pi over 2 is 0. So I'm going to rewrite this over here since I ran out of space. So this becomes 7/3 negative 1, and then we have minus 1. So this is 7 over 3 times negative 2. So it's going to give me negative 14 over 3. So that is my answer for this one. All right, let's try this one. I think this was an example in y'all's textbook. We're going to compute this integral over the region. Now again, hopefully you guys can appreciate why we're learning polar coordinates, because, you know, if you were to try to if you're trying to integrate this in rectangular coordinates, it'd be really ugly, and I wouldn't know how to do that. You know, maybe you could do like could you do a U substitution? I'm really not sure. But the point is that we can make some simple substitutions to make this a lot cleaner to work with. So okay, so you know, I'm trying to find the integral over this region, so I have a double integral. And maybe this region isn't too bad because it tells me my radius, so the starting radius of the region is 1, right? That's the circle with radius 1, and then it goes up to a circle with radius 2. So I'm going from r equals 1 to r equals 2. And how about theta? Where is theta varying? Well, this region starts on the positive x-axis. That starts when theta is equal to 0, and it includes everything all the way up to, it says theta equals pi over 4 is this angle right here. So we're going from theta equals 0 to theta equals pi over 4. And what I'm integrating is this guy right here. Okay, so what I'm going to do is I'm going to use the fact that x squared plus y squared equals r squared and make that substitution. So this becomes 1 over r squared to the 3 halves. And 2 to the 3 halves, if you multiply that, that just becomes r to the 3. So this is 1 over r to the 3, which is r to the negative 3. And that's it. So we're just integrating r to the negative 3. Now don't forget this r that's hanging out. This whenever we're doing dA, right? Whenever we're doing dA, we want to replace it with r dr d theta. Don't forget this r. I always forget. That's why I'm telling you guys to not make the same mistakes as me. So, now that we have this, we can multiply that. R to the negative 3 times r to the 1. Well, negative 3 plus 1 is negative 2. So this becomes r to the negative 2 dr d theta. We're going from 1 to 2 with the radius, and we're going from 0 to pi over 4 for theta. Alright, let's get down to business to defeat the Huns. I don't know if you guys are getting this Mulan, all my Mulan references. I don't know if I've had multiple, I don't know, I feel like I should have more Mulan references if I don't already. Mulan's a great movie. Anywho, let's get down to business and integrate this thing. Now look how easy this is as opposed to this. See? You see why polar coordinates are so useful? Okay. So let's go ahead and integrate this. Add 1, so we get r to the negative 1, divide by negative 1. We're going from 1 to 2. And if I plug in 2 for r, we get 2 to the negative 1 over negative 1 minus 1 to the negative 1 over negative 1. What is this? Let's see. So this is going to be negative 1 over 2. Like, what is this? This is going to be just plus 1. So negative a half plus 1 is just a half. Right? 1 minus a half. And now we need to integrate it with respect to theta, since we just did r. Okay, so let's go ahead and we're going from 0 to pi over 4, and this is d theta. So when I integrate that, it just becomes 1/2 theta, and I'm going from 0 to pi over 4. So 1/2 times pi over 4 is pi over 8, and then minus 0, of course, is just 0. So our answer here is pi over 8. Okay, so we want to decide whether to integrate using polar or Cartesian, aka rectangular coordinates. Write an iterated integral for an arbitrary function f of xy over the region. Okay, so here we have a region that we're integrating on. Can't speak today. And we're going to assume that the function itself and the region are going to be, you know, companions in the sense of, like, if the region is good to integrate on rectangular coordinates, then the function itself is going to be easy to integrate. So we have a region that's rectangular, and so it makes sense to use the rectangular or the Cartesian coordinates here. Now let's check out our bounds. So here's our arbitrary function. We're going f of xy, and we can do dy dx or dx dy. It really doesn't matter. But for x is varying from x equals 1 to x equals 3. And notice that x doesn't depend on y at all. X just depends on itself. So we don't have to write x in terms of y. So we're going from 1 to 3. And for the y value, we're going from negative 1 to positive 2. Okay, so this is... we have our region right here. We're integrating an arbitrary function, and maybe I should have included the y here, f of xy. And so there it is. Now let's take a look at this. Now we have a circle, okay? So whenever you see circles or curvy things, you should think polar, okay? Arcs, circles, polar coordinates. So let's go ahead and use polar coordinates here since we have a circular region. So remember that polar coordinates, we have r's and thetas, and my arbitrary function, instead of f of xy, we're going to have instead of x, we're going to have r cosine theta. Instead of y, we're going to have r sine theta. And then we can't forget that instead of dy dx, we can write r dr d theta. Okay? So now let's figure out the bounds. So for the radius, this set right here, we can say, well, I can go out from a radius of 0, right, all the way at the origin to a radius of 3. So we're going from 0 to 3. And for theta, we're sweeping out the entire circle, so we're going from 0 to 2 pi. So that is my answer there. All right, what should we use here? Rectangular or polar coordinates? Well, I see a bunch of straight lines. I don't see any curves. So if that's the case, then you should probably use rectangular coordinates or Cartesian coordinates. So that's what we're going to do. We're going to use Cartesian coordinates. So we have our function f of x, y. And our lower bound, our floor, our y value seems to depend on x. Right? Seems to be a function in x. Right? We have a lower bound. This is our lower bound for y. This is our upper bound for y. So we can see that the upper bound is 3, and we can do dy dx. What's the lower bound? Well, let's go ahead and figure out the equation of this line. It's a function of x. We can see that this line is going to cross the y-axis at -1, so our y-intercept is -1. And we can see the slope in a couple of different ways. One way to see it is the rise over run way. If we start here and we rise up 1, and then we run 2, right? So we rose up 1 and to the right 2, so that means our slope is 1/2. And so with these two things, the line that describes this little segment right here is going to be 1/2 x minus 1. So that's my lower bound for y. It's a function of x. Okay, what about x's? Well, we can just use the left and the right bounds for x. So we're starting at x equals 0. And our right bound for x is 2. So we're going from 0 to 2. So this would be our answer here. All right, so should we use Cartesian or polar coordinates for this integral? Well, we have some curve to it. We have arcs, so that tells me that we should use polar coordinates. Okay, so we are going from r equals what? Well, it looks like we're starting right here at r equals 1. So starting at a radius of 1, ending at a radius of 2. So we're going from 1 to 2. And then for theta, well, this sweeps out. This starts at pi over 2. Right? This starts at pi over 2, and it sweeps out to pi. So we're going from pi over 2 is my minimum angle to pi. It's my maximum angle. And my arbitrary function is going to be f of xy, which becomes f of r cosine theta, r sine theta. And then I have to tack on the r, dr, d theta. Okay, so that's my answer there. All right, now we'll go in the opposite direction. We want to sketch the region of integration. So we have some random function, who knows what it is, but everything's in polar coordinates. We can see r's and thetas are everywhere. And these are going to be our bounds. So let's go ahead and sketch the region based on this. This is my region. Well, for theta, I'm going from negative pi over 2 to pi over 2, right? Theta comes first. And then for r, I'm going from 0 to 4. So that's going to be the semicircle with radius 4. My r is equal to 4. And we can shade all of this region. So this is my region of integration. Convert to polar coordinates and evaluate. So right now we're in rectangular coordinates. We want to get all of this stuff in terms of r's and thetas. So what we need to do is we need to use our bounds as clues of what r and theta could like where they could vary. So the first clue is that y is varying between negative root 1 minus x squared and root 1 minus x squared. So let's write that as our first clue to find r and theta. So we have that y is going to be bigger than or equal to negative square root of 1 minus x squared and less than or equal to square root of 1 minus x squared. So that is our first clue. And the second clue that we have, and from the clues we need to get other information, but the second clue is that x is going to vary from negative 1 to 0. So x is going to be bigger than or equal to negative 1, less than or equal to 0. Okay, now how can we gather information about r and theta? Well, we need to work with what we have. You know, we want to come up with something that's in terms of x squareds, y squareds, r squareds, so that we can actually see what's going on. Now, this piece of information is actually going to give me theta. Let's actually work with this guy first. He looks easier to work with. Now, x is the same thing as r cosine theta. So r cosine theta is between negative 1 and 0. And if I divide everybody by r, if I divide that by r, it's just 0. So I get cosine theta is less than or equal to 0, greater than or equal to negative 1 over r. And r always has to be positive. Therefore, this fraction is always negative. Okay, so what does this tell me about theta? It tells me, okay, it says cosine is going to be smaller than or equal to 0, and at the same time, it's going to be bigger than or equal to negative 1 over r, where r is our radius. So basically what it's saying is that it can either be 0 or negative. Now, where is cosine negative? Cosine's negative in quadrants 2 and quadrants 3. Sorry about that. Cosine's negative because the x value is negative in both cases. So this is xy. Up here we have xy. So cosine's negative, and cosine also could be 0. So it could be that we're on this axis pi over 2, or we're on this axis 3 pi over 2. And it could also be anything within this region right here. Okay? So theta, because cosine varies between negative 1 over r and 0, my angle is going to vary between pi over 2 and 3 pi over 2. Okay, so we know that from this clue right here, theta is going to vary between pi over 2 and 3 pi over 2. So now we just need to determine where our radius is going to vary. So now that I used up that clue, let's look at the first clue. What I'm trying to do is introduce a radius. Okay, I want to introduce a radius into this clue. I want to introduce an r so that it can tell me something about the radius. Now, what you should be thinking of is this identity x squared plus y squared equals r squared. That identity has x squared, y squared, and r squared. So how do I get an r squared from that? Well, I have x squared, so I might as well square that y to get that little component in there. So if I square everybody, well, I can actually, I can break this up a little bit. I can say, well, y is bigger than or equal to negative 1 root 1 minus x squared, and it's less than or equal to square root of 1 minus x squared. So if I square this, I get y squared is bigger than or equal to 1 minus x squared when I square this thing, right? Because this is going to be negative 1 squared is positive. And then I get over here, if I square both sides, I get y squared is less than or equal to 1 minus x squared. So this is the information that I'm given. If something is greater than or equal to something and at the same time is less than or equal to something, it must be that it's equal, right? Because it can't be greater and less at the same time. It has to be equal, right? So what we have now is, instead of, this inequality, now we have y squared is equal to 1 minus x squared, right? It's greater than or equal to that, but it's also less than or equal to that, and the only way for these two things to be simultaneously true is if it's actually equal to, okay? So going ahead to isolate my sorry, I'm like, I don't know why I can't get my words out right now, but isolating this number 1, if I add x squared to both sides, I get y squared plus x squared equals 1, and so this is a circle centered at the origin of radius 1, so we get r squared is equal to 1, making that substitution in there. Taking the square root, we get r is equal to 1. So this is our region is a circle of radius 1 centered at the origin. Okay, so what are my bounds going to be for r? Well, I'm going to be between 0 and 1 because my region is that circle centered at the origin. Okay. And now that I have that, I am good to set up my integrals. So I'm going from theta goes from pi over 2 to 3 pi over 2. R is going from 0 to 1. This x right here is going to turn into r cosine theta. And this dy dx is going to turn into r dr d theta. Alright, that's this dy dx. So let's go ahead and figure this out now. Figure out what this is. Okay. Alright, so since I'm integrating with respect to r first, I'll combine these two by multiplication, saying this is r squared cosine theta, dr d theta, and I'm going from 0 to 1, and then from pi over 2 to 3 pi over 2. So with respect to r, this becomes r cubed over 3 cosine theta, and I'm going from r equals 0 to r equals 1 from these bounds. So plugging in 1 for r, I get a third cosine theta, minus plug in 0 for r, and I get minus 0. So now I have this guy, and I'm integrating him from pi over 2 to 3 pi over 2 with respect to theta. Okay, so now I can go ahead and pull out that 1/3 in the front. And now if I integrate cosine of d theta, so What do I have to differentiate to get cosine? Well, sine. So that's going to be my answer there. I'm going sine theta from pi over 2 to 3 pi over 2. And I still have that 1/3 in the front there. Okay, so we have a third sine of 3 pi over 2 minus sine of pi over 2. So this is a third times -1 minus 1. So it's -2/3 is our answer there. Okay, so let's convert to polar coordinates and evaluate the double integral here. Okay, so our bounds for r and theta are going to be given to us right here. And so what we see, our first clue tells us that x is going to vary between y and square root of 4 minus y squared. And this piece right here is telling us that y is going to vary between 0 and square root of 2. So let's see what kind of information that gives us. Okay, so if I look at this first compound inequality, what I can do is I can separate them. That might make things a little bit easier. If I do that, I have x is greater than or equal to y, and I also have x is less than or equal to the square root of 4 minus y squared. Okay, so x is greater than or equal to y. Well, if I now change into polar coordinates, x becomes r cosine theta, and y becomes r sine theta. And if I divide both sides by r, I get cosine theta is greater than or equal to sine theta. If I divide both sides by cosine theta, I get 1 is greater than or equal to sine theta over cosine theta. So that's going to be tan theta. So I have tan theta less than or equal to 1, which doesn't give me a whole lot of information, right? So tan theta less than or equal to 1, well, there could be, there's not really a good bound that we can put on that for theta, but let's go ahead and look at this expression right here. Now, if I square both sides, what I'm going to get is x squared less than or equal to 4 minus y squared. If I add y squared to both sides, I get x squared plus y squared. It's less than or equal to 4. And I know that x squared plus y squared is equal to r squared in polar coordinates. So r squared is less than or equal to 4. Taking the square root, I get r is less than or equal to 2. So I have some sort of bound for my radius. This guy, I do have a little bit of a bound for theta as well, but this piece isn't telling me a whole lot about where theta can vary. Now, so that was all the information that we gathered from this first piece right here. Okay, so these two things that I have boxed and circled. Now, what about this right here? What is this telling us information about? Well, we have y varies between 0 and radical 2. And if I change y into polar coordinates, I have r sine theta is less than or equal to radical 2, greater than or equal to 0. If I divide by r, I get sine of theta is less than or equal to radical 2 over r, greater than or equal to, 0 divided by r is just 0. So sine theta is between 0 and radical 2 over r. Now, I know from right here that r has to be less than or equal to 2. Okay? So that means that I have sine of theta is going to be between 0 less than or equal to root 2 over 2. So this is some good information to have, right? Because now I have bounds for theta. It says, well, sine theta is going to be between 0 and root 2 over 2. And so theta, therefore theta, so since the sine is going to be bigger than 0, so sine is positive, but it's less than or equal to root 2 over 2, that means that we have to be in quadrant 1, and specifically theta right here, what angle has a sine of root 2 over 2? Remember, sine is our y value. So which angle has a sine of root 2 over 2? Well, that has to be pi over 4. Okay, so theta is going to vary between 0, because sine of 0 is 0, and pi over 4. Okay, so we already know what our bounds for theta are going to be, 0 to pi over 4. And now we've exhausted all of the information that we were given. We have r is less than or equal to 2. So that means that r, because r can't be negative, r is going to be between 0 and 2. Okay, so these are going to be our bounds for integration. And all that's left to do is put this guy, xy, dx, dy, in polar. So let's go ahead and do that. So we initially start with this. We have xy, dx, dy. We want to change this to polar. So x is r cosine theta, and y is r sine theta. And the dx dy is dA, so that's going to change to r dr d theta. Okay? So I'm integrating from, well, my r bounds, I'm going from 0 to 2. And then my theta bounds, we're going from 0 to pi over 4. Okay, so now this is my problem right here that I need to integrate this guy now. Okay, so we're going with respect to r first, so I'm just going to multiply these r's out. I have 3 of them. So this becomes r cubed cosine theta, sine theta, dr d theta, going from 0 to 2, and then 0 to pi over 4. Okay, so let's integrate with respect to r first, leaving cosine sine as a constant. We get r to the 4th over 4 cosine theta, sine theta, and we're going from 0 to 2. R equals 0 to r equals 2, since the dr comes first. Okay, so if I plug in r is 2, I get 2 to the 4th over 4 cosine sine minus, well, if I plug in 0 for r, it just all goes to 0, so this is it. 2 to the 4th is 16, so 16 over 4 is 4, so I'll just change that to a 4. So this is what I'm integrating now, from 0 to pi over 4. And this is with respect to theta. Now at this point, we can't integrate this straight away. But what we could do is we could do a few things. My instinct is to use a trigonometric identity. And that identity is a double angle identity, right? Because I'm in this position and I'm like, okay, well, what am I going to do here? You could do that. You could do a U substitution right off the bat if you wanted to. What I'm going to do, I'm going to use this trig identity. And that trig identity is that the sine of 2 theta is equal to 2 cosine theta sine theta. I'm going to use this identity. This is a double angle identity that you probably saw a bunch of this in trig, maybe a little bit in calculus, but but what I'm recognizing is that this, I see a 2 cosine sign. I see a 2 cosine sign because 4 is 2 times 2. So 2 times 2 times cosine sine. And that's going to make this simpler to integrate if I use that identity. And of course, I ran out of room. So I'm going to work up here, erase some things. Let's get some scratch work going. Okay, so here's where I'm at. I'm going from 0 to pi over 4. I'm going to pull out one of those 2's in the front, and then I'm going to replace this 2 cosine sine with this double angle identity right there. So I'm going to replace that with sine of 2 theta, and I am integrating with respect to theta. Now this, I can do a pretty straightforward u substitution. So I can let u, if you guys remember this from Calc 1 or Calc 2 or whenever the last time you saw it, you probably saw it in Calc 2 as well, even if you didn't take me. But what we're going to do is we're going to let u equal 2 theta. And if we take the derivative, both sides, let me erase some of this so I have some more room. What I get is du is equal to 2 d theta. Remember how we did those u substitutions? So if I isolate d theta by dividing both sides by 2, I get du over 2 is equal to d theta. So let's go ahead and change everything in terms of u using those things that I boxed. I'm talking about right here. If I change everything into terms of u, well, then I get sine of u. And instead of d theta, I get du over 2. And I'm going to go ahead and bring that 1/2 to the front so that this just clears to 1. Okay, hopefully you guys can see that when I bring that clears to 1. So I'm just going to kind of erase everything right here because that all clears to 1. And now this is simple. So if I integrate this, I'm going to get negative cosine of u. And now I can plug in my u back, which was 2 theta. And I'm going from 0 to pi over 4. So this becomes negative cosine of 2 pi over 4 minus negative cosine 2 times 0 is just 0, cosine of 0. And now I can simplify. So this becomes pi over 2. Cosine of pi over 2 is 0. So this becomes 0. Cosine of 0 is 1. So this becomes a positive. These double negatives become positive, and I end up getting 1 as my answer there. All right, so there's my answer. Okay, so we want to evaluate this integral over the region given here. It says R is the first quadrant between the circles of radius 1 and radius 2. So this is nice that they give us the region kind of it's right out there. You know, there's no like weird inequalities that we have to interpret or anything. So we can go ahead and just like sketch our region. And here's X and Y. And so it's going to be in the first quadrant. And it's going to be between the circles of radius 1 and radius 2. So maybe something that looks like this, a little band. This is our region R. Okay. All right, so now it's not too bad to set up the integral now. So we know what our region is, we know what theta is, and we know what R is going to vary between. It says R is going to vary between 1 and 2. So we have 1 to 2. And theta, since we're in quadrant 1, we're starting at an angle of 0, and we're ending at an angle of pi over 2. So theta is going to vary between 0 and pi over 2. And now all that's left to do is change this guy, and of course the dA, into polar. So x squared, and you know, the thing is we can't replace this with r squared because of that minus sign, the annoying minus sign. So x squared we can replace with r cosine theta squared minus y we can replace with r sine theta, and that's squared. And the dA we're going to replace with r dr d theta. Okay? So now we can clean this up a little bit. Let's see, if I square the r cosine, I get r squared cosine squared. If I square the r sine, I get r squared sine squared. And this is all multiplied by r dr d theta. And I'm going to write those bounds in just a little bit, but let's kind of clean this up first before we start doing that. Well, maybe I'll just write it just because. Okay, so what can I do? Well, I can factor out an r squared. So then I get cosine squared theta. I forgot my theta. Minus sine squared theta. And that r on the outside can be multiplied by the r in the front, so I'm going to just write this as r cubed. And this is dr d theta. So we're going from 1 to 2, and then from 0 to pi over 2. So let's go ahead and integrate with respect to r first. So when I do that, I just get r to the 4 over 4, and this cosine squared minus sine squared is simply a constant. Okay, and I'm going from 1 to 2. So 2 to the 4th over 4 cosine squared minus sine squared minus 1 to the 4th over 4 cosine squared minus sine squared. Okay? So what is this going to become? Well, let's see. So this is going to be, if I factor out a cosine squared sine squared minus sine squared, I'm going to be left with that times 2 to the 4th over 4 is 4 minus a 4th. Okay, so 4 is the same thing as 16 fourths. So 16 fourths minus 1 fourth is 15 fourths. So that's going here. All right, so now I need to integrate with respect to theta. So I'm going from 0 to pi over 2. And this is going to be with respect to theta. So what I can do at the start is I can factor out the 15 over 4. Make that a little bit cleaner on the inside. So then I get, maybe I don't have to put this in parentheses anymore. I get cosine squared minus sine squared. And at this point, you know, it's not, it might not be clear what to do because U substitution isn't going to work. And I don't know about integration by parts either. You might be able to do something there, but I think, you know, the easiest thing to start with when you get into a situation like this, the first thing to check is if you can use any trig identities to replace and make things simpler. So what I'm imagining is the identity, let's see, what should I do? Well, how about the Pythagorean identity? How about this? Pythagorean identity is cosine squared theta plus sine squared theta is equal to 1. And if I can convert everything in terms of either sine squareds or cosine squareds, then I'm on my way to a simpler expression. And that's what I'm trying to do here. So what I'm going to do is I'm going to isolate sine squared by subtracting cosine squared from both sides. And you guys have seen this before in trig or in calculus 1 or 2. So we get sine squared is equal to 1 minus cosine squared. Okay, so that's what I'm going to replace right here with 1 minus cosine squared. So let's go ahead and do that. So this is going to become cosine squared minus 1 minus cosine squared theta d theta. All right. So let's see. So I get 15 over 4, 0 to pi over 2, cosine squared minus 1 plus cosine squared d theta. So this becomes 2 cosine squared theta. And this looks like an identity. I believe this is an identity. Let's double check to see what this is. I'm being a little bit lazy here. I'm just gonna look at my identity list. And we're gonna hope that it's a double angle identity, because that would be a nice U substitution. Let's see. Let's see if it works out. 2 cosine squared minus 1. Okay, good. So this is a double angle identity, thank God. We have a double angle identity. Let me write up here. That 2 cosine squared theta minus 1 is actually equal to cosine 2 theta. This is really handy for U substitutions. So let's go ahead and make that substitution. So we have 15 over 4, 0 to pi over 2, and then we have the double angle cosine of 2 theta is actually equal to all of that in red. Okay, now it's just a U substitution problem. We're going to let U equal 2 theta, and so du is going to be 2 d theta, and therefore d theta is equal to du over 2. So, subbing this in and this idea in right here and right here, we get the following. We get 15 over 4, going from 0 to pi over 2, cosine u, du over 2. And I'm going to factor out the 1 over 2 to the front. So when I do that, I actually get 15 over 8 when I do that factorization. 0 to pi over 2, cosine u, du. And now I'm going to have to erase some stuff because I can't go down any further. Let's go ahead and erase some of this stuff. Alright, so let me write it up here. So we have 15 over 15 over 8, 0 to pi over 2. I don't know why that 0 was put there. Cosine u du. Alright, so the antiderivative of cosine u is going to be sine of u. So we have sine of u, and remember, u was 2 theta. So we have sine of 2 theta from 0 to pi over 2. And we still have that 15 over 8 in the background over there. Okay, so evaluating at pi over 2 and 0, we get sine of 2 pi over 2 minus sine of 2 times 0 is 0. Well, 2 pi over 2 is pi. Sine of pi is 0. 0 minus 0 is 0. 15 over 8 times 0 is 0. So our answer is 0. And it's not really a coincidence or surprising why that's equal to 0. You know, if you were to examine this graph on Desmos, there's some symmetry on the region of integration. And what do I mean by that? Well, I'm not going to go into it. I'm not going to pull up GeoGebra and everything, but I'm going to encourage you guys to look at it. But I do want to talk a little bit about Calc 1 and how when we had something that looked like maybe like this. Oh, that's a terrible picture. I'm trying to make this symmetric. So when we had something like this and we were computing the integral, we got 0. And the question is why? Well, it's because of the symmetry right here along the along the interval of integration. So what I'm encouraging you guys to do is to take a look at that function in GeoGebra, take a look at the region of integration, and notice the symmetry that is at play here. That's why this thing is going to ultimately be 0. But anyway, thank you guys for watching. I'll see you guys next time.